Friends, welcome to the 32nd lecture. We are continuing with the discussions on curved beams. We have derived equations in the last two lectures on curved beams with small initial curvature and large initial curvature. We have derived the expression for Winkler-Bach equation. We will continue to do the discussions to find the stresses in extreme fibers of curved beams with large initial curvature in this lecture. To recollect back, we have a cross section whose CG is marked. This becomes my axis at which the radius of curvature is located. So, the centroidal axis is located at distance r, whereas the beam is subjected to a bending moment of this nature, which causes tension in the extrados and compression in the intrados on extreme fibers, the applied moment being m. Therefore, this makes the neutral axis to shift to the bottom, that is towards the center of curvature. So, this is by neutral axis, this is my centroidal axis. With curved beams of large initial curvature, we have already said that the centroidal axis and neutral axis will not coincide, and the stress variation along this section is hyperbolic. Since they are not equal, the neutral axis is not coinciding with the centroidal axis. So, the stress variation is hyperbolic. Therefore, the Winkler-Bach equation is useful to estimate the stresses in curved beams with large initial curvature only at the extreme skin layers. So, please note this equation can give you the stresses only at the extreme points. So, we call this as R intrados and we can call this as R extrados. We can simply say this as R neutral axis. This can also be read as R outer. From the CG, the extreme fiber distances are HO and HI. You can take any point, maybe here, which is at the distance of y from the centroidal axis. For this classical terminology, we said stress is given by m by AR 1 minus small m y by r plus y, which is called the famous Winkler-Bach equation, which we derived in the last lecture. Now, m depends on the geometry, shape of the geometrical cross section, which is a section property. In fact, I should say it is a property of designer's choice. I can quote a parallel example of this. For example, in plastic design, to enable maximum load capacity, designers use sections with large shift factors. Similar to this, m is a cross sectional property which is a designer's choice to limit the stresses in extreme fibers in curved beams with large initial curvature. One can choose the cross section accordingly or the value of m to suit the appropriate cross section. There is alternative form of this equation 1, which we also derived in the last lecture. Stress can also be said as m by A e of y plus e by y plus r, where e is the offset of neutral axis from the centroidal axis measured towards the center of curvature. That is, this is my E. Now, considering equation 2, one can always derive specific stress equations for intradas and extradas to find maximum stresses in the extreme fibers. So, look at the cross section here again. The distance of the extreme fiber, one is what we call as Hi, which is intradas. The other one is what we call as H0 or HO, which is the extradas. Basically, this distance is essentially this. We also know this is compression and this is tension. For the given assumption that the neutral axis shifts towards the center of curvature, tensile stresses are positive. So, with that assumption, I want to find intradas. Stress in the maximum fiber will be given by m by AE. So, y in this case going to be minus Hi minus Hi. So, I can rewrite this equation as m by Ae minus of Hi minus E by Ri. If you look at the figure, R minus Hi will be actually equal to Ri. Okay. Here negative sign indicates that the stresses will be compressive. Similarly, stress for extra DOS is m by Ae. Y in this case going to be Ho plus E R plus Ho, which I can say m by Ae E plus Ho by R plus Ho can be said as R 0. So, the positive sign indicates that stresses are tensile in nature. So, extra DOS has got tensile stresses and intra DOS has got compressive stresses, which is evident from this equation of finding out stresses on extreme fibers. Please note, this equation is useful only to estimate the stresses on extreme fibers, because the stress along the cross section is varying hyperbolically. So, this equation does not give me the stress variation along the depth. This can give me the stress only in the extreme fibers of the given cross section. Okay. So, now having said this, it is clear that stress is a function of m. So, one need to estimate this value m for various cross sections which are used commonly in curved beams. If you look back the derivation, we already know that m A is actually integral of y by r plus y dA for the entire range. So, using this equation 3, we are now going to derive the cross sectional property m for various geometrical shapes of the cross section. Let us take a circular cross section. Let us say this is my axis of reference where I am going to mark my center of curvature. Let us say this is my centroidal axis . So, that is my centroid, and this is going to be my neutral axis. We know that this shift is E, and we also know that this distance is R. Let us take a fiber which is at an angle theta. The radius of the circular cross section is small r, and let that fiber be at a distance y from the centroidal axis, and let this be dy. Let us introduce one more variable, which is small v from here. So, area of the elemental strip dA will be equal to r cos theta twice of that multiplied by dy. We also know y is r sin theta. Therefore, dy is r cos theta d theta. Hence, dA will be now 2 r cos theta d theta, which makes it as 2 r square cos square theta d theta. We now know MA is integral y by r plus y dA for the whole area. I can write this as y can be said as v minus r, and r plus y is v dA, which is now integral dA A minus r integral dA by v. Let us pick up this integral dA by v. Let us do this. dA already we said it is 2 r square cos square theta d theta by v, which is 2 r square cos square d theta. V is r plus y, which is 2 r square cos square theta d theta by r plus r sin theta. Integral dA by v will be now integrated from the limits minus pi by 2 to plus pi by 2, 2 r square cos square theta d theta by r plus r sin theta. Let k be expressed by a ratio r by r. So, integral dA by v dA will be actually equal to 2 r square by r minus pi by 2 plus pi by 2 cos square theta d theta by k plus sin theta which is now 2r limits cos square theta by k plus sin theta d theta, which can be expressed as 2r 1 minus sin square theta by k plus sin theta d theta. Let us divide this. One minus sin square theta k plus sin theta. Let us say minus sin theta, which makes it as minus k sin theta minus sin square theta, which says 1 plus k sin theta. So, again k, so I get k plus k sin theta, which gives me 1 minus k, this is k square, 1 minus k square. So, therefore, I can now express the integral dA by v as 2r integral minus pi by 2 plus pi by 2 k minus sin theta plus 1 minus k square by k plus sin theta the whole of d theta. Which can be now said as 2r minus pi by 2 plus pi by 2 k minus sin theta d theta, let us say minus 2r minus pi by 2 plus pi by 2 k square minus 1 by k plus sin theta d theta. Let us take this integral I 1 and this integral I 2. Let us take I 1 first. Integral k minus sin theta d theta minus pi by 2 plus pi by 2, which will be k theta plus cos theta minus pi by 2 plus pi by 2. So, k pi by 2 minus of minus pi by 2 plus 0, because cos pi by 2 has no value. So, this gives me k pi. Therefore, 2r k pi is the value of my first term. I will call this as equation number 4. Let us say this is 5. Let us pick up I 2. I 2, the second integral, is actually integration minus pi by 2 plus pi by 2 k square minus 1 k plus sin theta d theta. In fact, the integral actually is minus pi by 2 plus pi by 2 k square minus 1 d theta by k plus sin theta. I can express this integral as similar to dx by a plus b sin x minus pi by 2 plus pi by 2, where a is k and b is unity. Now, this has got a standard relationship which is given by twice of root a square minus b square tan inverse a tan x by 2 plus b by root of a square minus b square limits minus to plus pi by 2, and of course, here x is theta. So, 2 by root of k square minus 1 tan inverse of k tan theta by 2 plus 1 by root of k square minus 1 applicable to limits minus pi by 2 to plus pi by 2, which can be then simplified. 2 by root of k square minus 1 tan inverse of k plus 1 by root of k square minus 1 minus tan inverse of minus k plus 1 by root of k square minus 1 after substituting the limits, which will then simplify to 2 by root of k square minus 1 of pi by 2. Therefore, which I call as equation number 6. Substituting 5 and 6 in equation 4. So, integral dA by v will be 2 pi r k minus 2 r k square minus 1 pi by root of k square minus 1, which tells me 2 pi r k minus root of k square minus 1. We know k is r by r, let us substitute that r by r minus root of r by r square minus 1, which can be also said as 2 pi r by r root of r square minus r square by r square. So, dA by v integral is 2 pi r minus root of r square minus r square. So, equation number 7. Therefore, MA is integral dA minus r integral dA by v. So, MA is pi r square minus r into 2 pi r minus root of r square minus r square. So, therefore, M is pi r square by A minus r into 2 pi by pi r square of r minus r minus r square. So, this becomes 1. So, this is 1 minus twice of r by pi r minus root of r square minus r square is r square. So, simplifying further, m will be 1 minus 2 r by r the whole square plus, there are 3 terms here in this equation, first term, second term and third term, 2 r by r square. So, first term, second term, third term. So, third term will be plus twice of r by r root of r by r the whole square minus 1. So, that is going to be my cross sectional property parameter m for a circular cross section. Equation number 8. Now, I want to find the eccentricity of neutral axis with respect to CG axis, that is to find E. We know MA is integral dA minus R integral dA by V, that is MA is A minus R integral dA by V A. So, m is 1 minus R by V dA by V. Also, E is m by m minus 1 into R. So, E is 1 minus R by A integral dA by V divided by 1 minus R by A integral dA by V minus 1 the whole multiplied by R. So, this 2 goes away. So, R times of 1 minus R by A integral dA by V divided by minus R by A integral dA by V, which I can say as E is R minus A by integral dA by V. So, using this relationship, which is equation 9, let us find R in our case. So, we know E is R minus A by integral dA by V. So, we already know that integral dA by V for the circular section is actually 2 pi r minus r square minus r square. Therefore, E is going to be r minus pi r square 2 pi r minus root of r square minus r square. By simplification, E will be r minus r square by twice r minus root of r square minus r square. So, I get E is equation number 10. So, both E and M are geometric parameters which depend on shape of the cross section. As you can see here, the variables are radius of curvature, then small r, which is the radius of the section, and capital R is the radius of curvature. If I know these two parameters, I can find E as well as M. Okay. That is how we got E and M, which are actually geometric parameters for a circular cross section. Let us do this for a rectangular cross section. Let us take a rectangular cross section. So, this is my O axis or plane. The breadth of the cross section is B. The centroidal axis is at a distance r. We take a strip which is at a distance y from the centroidal axis. The neutral axis of course is located at a distance E. This is my neutral axis. Then we say that the intradas at a distance r1 and the extradas is at a distance r2 and the dimensions say h by 2 and h by 2. Let us say this distance is V from here and this thickness is, let us say, we know that dA is B dy, MA is integral y by r plus y dA, which is V minus r by V of dA, which is integral dA minus r integral dA by V is MA, which will be from the limits r1 to r2. So, which will give me A minus r B natural logarithm of r2 by r1, because dA is actually B dV. So, therefore, M is 1 minus r by A B natural logarithm of r2 by r1. which can be also said as 1 minus r by a b natural logarithm of r 2 can be expressed as r plus h by 2 and this is r minus h by 2, the equation number 11. So, once I know m, I can always find E using the relation which I already derived. Let us do it for a T section. Let us say this is B 1 and this is B 2, the CG is somewhere here, whereas this is my OO plane and this becomes my R and this is my R 1, this is my R 2 and let us mark this as R 3. Let us take a strip at a distance y from the centroidal axis. Let us take that value of the strip to be located at V from the plane of center of curvature. We know that M A is integral by r plus y d A, which can be integral V minus r by V d A, which can be integral d A A minus r integral 1 by V d A, which I say as A minus r times of integral B 1. The limits for B 1 are the piece 1 varies from R 1 to R 2, which is d V by V minus R. The second piece B 2 integral again d V by V, but the limits varies from R 2 to R 3. So, I can say now as A minus R B 1 natural logarithm of R 2 by R 1 minus R B 2 natural logarithm of R 3 by R 2. Therefore, M is 1 minus R by A of B 1 log R 2 by R 1 plus B 2 natural logarithm R 3 by R 2. Equation number 12. Also, we know that E is M by M minus 1 into R. So, let us substitute that E is going to be equal to R of 1 minus R by A B 1 log R 2 by R 1 B 2 log R 3 by R 2 divided by 1 minus R by A B 1 log R2 by R1 B2 log R3 by R2 minus 1, which gets cancelled. So, this can be said as R times of 1 minus 1 by R by A of this expression, which can be said as E is equal to R minus A by B1 log R2 by R1 plus B2 log R3 by R2. Equation number 30. So, friends, we understood that for curved beams with large initial curvature, centroidal axis and neutral axis will not coincide. This is due to the fact that the stress in the extreme fibers are not equal. So, it is important to locate the neutral axis, which depends on sectional property M. So, we found out for different cross sections, for different shape of cross sections like circular, rectangular, T section, we determined or we rather derived M and E from first principles. Once I know these two parameters, I can always find the stresses in the extreme fibers using the standard Winkler-Bach equation, which we derived. We will also discuss these parameters for other shape of cross sections and also try to tell what would be the approximate variation of these stresses in extreme fibers compared to that of theory of simple bending in the next lecture. Thank you very much.